Okay, welcome everybody. We're happy to have today Robinson Mancilla. He's a Chilean guy, but from the University of Santa Barbara, and he will speak about near-extremal dynamics away from the horizon. So, Robinson, all yours.
Cool, thanks. So this is a practice for my PhD defense. So for the reason there will be some extra slides that are unrelated to this title, but it's because of
So,
that.
so we have the permission to ask many questions and
Yeah,
be
yeah.
well mercy.
Will appreciate if you ask me all of the possible questions. So when I give this real talk, I am able to
Okay.
answer. Um, okay, so this is the outline. I'm gonna say some prelude related to my PhD. Then I'm gonna go to the motivation of this particular talk. A little bit, I'm gonna say a little bit of Schwarzian theory and the word identities, and then the word identities in higher dimension. Then I'm gonna provide a generalization of the so-called decoupled limit and a discussion at the very end of all of this. So the prelude is the following. As a PhD student, essentially I work in ADS-CFT, in particular in black hole physics. The statement is that essentially in certain classes of strongly coupled quantum field theory, with a large number of degrees of freedom in a fixed space-time, the same QFT can be described by a higher dimensional quantum gravity theory. So that's kind of my context of research. And these are kind of the articles that I went through during my PhD. Two with my advisor, David Bernstein, one a project by myself, and this project that I'm going to talk today with Alejandra Castro and Ioannis Papadimitriou from Athens University. And I hope so it's published on May. Okay, so this is the motivation. So I hope so that most of you have heard about the Schwarzian theory. Essentially, it's a universal effective field theory that describes the low energy physics of a broad class of systems. In particular, the SYK model, also random matrices, for what is important for me, higher dimensional charge or rotating black holes. And the gravitational dual of the Schwarzian theories is JT gravity. And among all of these different possibilities to UV complete JT gravity, to UV complete the Schwarzian theory, I'm just gonna focus on higher dimensional black holes. So there will be no discussion about core diagrams of SYK, neither ensemble average from random matrices. So it's just the standard ADS-CFT story. To provide more motivation about this project, one important results about the Schwarzian is that at very low temperature, the quantum fluctuations of the Schwarzian dynamics dominate over 3 levels. So quantum fluctuation becomes more important than classical contributions. And that is the result that inspired this paper of Luca, Joaquin, and Samir Murthy, that essentially at very low temperatures, the black hole partition function scales with T power 3 over 2, assuming that the black hole is non-supersymmetric. And that means that the extremal entropy of the classical result that we know for instance, in Reynolds-Nostrom is actually wrong. Like if you include a quantum effects, actually that entropy will go to 0. There is no degeneracy. In the case of supersymmetry, there is a degeneracy because of supersymmetry, and in that case, this statement is not true. But the point is that in those computations, they assume that you can do this computation of the gravitational path integral just focusing in fluctuations around the throat of the black hole and dropping everything else that is far away from the throat. And that is a huge assumption that we do actually in ADS-CFT in general. But you might ask the following question. It is possible to compute logarithmic corrections using the full black hole geometry at very low temperature without relying in the near horizon region. And there were two papers that tried to do this with positive evidence. That one is for Chiara Toldo and the other is for Joaquin Amashek and other people. And that paper, they did it for ADS3 CFT2. And also they have some numerical evidence that maybe this is possible doing it in higher dimension. But this is kind of a very discussion about thermodynamics. So now let's move on to something more dynamic. So instead of focusing on thermodynamics, let's ask the same question, or a similar question, but in the context of dynamics. So for instance, can the Schwarzian dynamics be derived from higher dimensional holographic CFT? That's what I'm going to talk today. And there is a similar question. If you are more like a fluid gravity guy, you can ask a similar question that is, given a perfect fluid effective action in higher dimension, is it possible to implement the decoupled limit to obtain the Schwarzian action? Here you will find immediately one problem is that these fluid effective action normally are not compatible with the smart formula. And in my solo paper, I essentially I solved that issue. I found a generalized effective action that is able to reproduce the smart formula. One important thing about these two questions is that I ask you to find a procedure from the UV theory that is able to reproduce the Schwarzian action in the IR. Because from the point of view just of symmetries and effective field theory, for sure, these statements are true. But one thing is the UV completion and the precise derivation of the Schwarzian dynamics. Another thing is to use effective field arguments and symmetries to argue that that must be the case. Okay. Is there any question up to this point? All right. So
sorry, Robinson, one question. I mean, when you mentioned this, that to try to make the analysis with the full geometry, then my question would be, you are relying then only on the fact that you're working in a special regime like low temperature to be able to do the analysis, or?
Yeah, no, it's more like that, because imagine you have a Reynolds-Nostrum black hole and you start to decrease a lot of the temperature. When then you focus in the near horizon region, you have to perform the decoupled limit. So there are two steps over there. It's not just that you are working a low temperature, but also you are throwing away a lot of degrees of freedom when you focus in the near horizon region. Like, because if you pick out a Reynolds-Nostrum black hole and you start to decrease the temperature, you won't see ADS2 cross S2 right away. You have to do something else.
Correct. Okay.
That's
okay.
that.
Thank you.
And because of that, because the geometry is more complicated, it's harder to do computations, available in higher dimensions. So in that sense, doing this approximation of going to the near horizon is very good. But it's still an approximation, and you're doing some assumption that you can do that.
Okay. Thank you.
Okay, good. So this is kind of the picture that you should keep in mind. So in the top line, I have the standard holographic duality between ADS4 and a CFT3. But then, for instance, in ADS4, you can work out the decoupled limit, and this IR dot represents the small black hole, and JT gravity is essentially a perturbation theory around that. On the other hand, and this is something that we understand very well, like that's the decoupled limit that we know. But then very low energy, you also have a new holographic dictionary between JT gravity and the Schwarzian theory. And the Schwarzian theory should be understood as a conformal perturbation around the IR fixed point. It's very important to recognize that the Schwarzian theory is not a CFT. It's conformal perturbation theory. So it's slightly different, okay? But the question is, can you give me a holographic CFT and work out some kind of RG flow and obtain the Schwarzian theory? That is the question that we want to try to deal with, okay? And this is not obvious that you can do it. If you are a believer of holography, for sure you will believe that this is possible. The problem is how you can do it explicitly. But there are certain obstacles that makes this a little difficult to deal with. So let me go back to the picture before. Here, as a sample, I pick out a CFT3. But the Schwarzian theory is one-dimensional. So you went from 3-dimension to 1-dimension. So you did some kind of dimensional reduction. So this decoupled limit from the point of view of field theory is some kind of energy flow across dimensions. So that is something slightly new with respect to other things that we know about RG flows. For instance, here you cannot argue using the C theorem of CFT2 or A theorem of CFT4, I think. Yeah, you cannot do that because those theorems just work when you keep in the same dimensions. Okay. Also, because this is related to some kind of conformal anomaly, you cannot argue using the top anomaly matching condition to say that you should have the same because this is protected for some topological reason. So this is harder because of that. You cannot rely on those tools. The other thing is that in the CFT3 in particular, there is not anomaly. There is no way that you can introduce an anomaly in that case. But when you do the couple limit of the RG flow, near the IR fixed point, an anomalous dynamics will emerge. So that's kind of unusual. The other thing is that you should notice that normally we don't have a Lagrangian description for this holographic CFT, except in very particular cases when we have a lot of supersymmetry. But in those cases, try to work out an explicit RG flow is out of the reach. Like for instance, ABGM or any equal-force emergence. That is too hard. So that is kind of challenges that we have from the point of view of field theory, but then there's other challenges related to gravity itself. So this famous reparametrization mode that we use to describe the Schwarzian theory is something that just emerged at very low temperature. It's not like in higher dimension you will see something like that. Okay, in the language of asymptotic symmetries, and higher dimension asymptotic symmetries are finite dimensional. Okay, so you cannot talk about Virasoro in 40. Okay, and the other thing is that this is the couple limit that we work out in gravity. Most of the time is defined on shell. You say, I'm gonna give you a particular black hole, like say ADS Reynolds Nostrum, and I wanna work out this decoupled limit. It's not off shell, like you are working with a particular solution, okay? And sometimes it can be made off shell, but it must restricted to the S-way sector. That means that you assume spherical symmetry and you dimensional reduce the Einstein equations and do some work over there. For our purpose, that is, we need to overcome those limitations. Okay. So
Robinson, sorry. Now I don't understand the point 3. Why don't you consider ABGM? You consider like a defect in ABGM or operator in ABGM, something like that?
The point is like, if we believe in holography, there is a sector of ABGM that is the Schwarzian theory. The point is like no one is so powerful to compute that explicitly. It's like more
okay,
a difficulty of technicalities than like a conceptual difficulty.
okay. But do you know what's the S-wave sector in the CFT theory? Because when you do the path integral in the gravity side, you take the S-wave sector, but you should do the same in the CFT, right?
Yeah, but the point is like you might try to do some S-Y sector. There are many things extra to consider. The theory becomes strongly coupled, and there are large degrees of freedom. And most of the time, all of the tools that people use is using supersymmetry.
Yeah.
In practice, you cannot do that. Like I asked to David Bernstein, that is expert in equal-force via Milt. He said you cannot just do it. It's too hard.
Okay. Thank you.
Maybe I hope so in the future people is able to do that, but it's just simple out of the reach currently.
Okay.
Actually, I think maybe when you have supersymmetric black holes, because nowadays there are a lot of tools from localization and others some kind of trace relation with supersymmetry. Maybe in those contexts you might dream to try to do this, but in practice it's just hard.
Okay.
So that means that what I'm gonna try to do now, and let me get back to my picture, is to generalize this decoupled limit and to become off-shell, and that is goes beyond the S-way sector, such that I can ask this question to gravity. I'm gonna say, gravity, please tell me what you are doing here. Okay, but in a way that I be able to compare this dot in the CFT3 with the Schwarzian theory rather explicitly. So I'm gonna do something like that, but in variables that I can compare very explicitly. So now I'm going to start with the Schwarzian action that I mentioned before. So this is the famous Schwarzian action. You have f of u is the reparametrization mode, which essentially is a temporal diffeomorphism in the theory. It's just one dimension. S is the Schwarzian derivative, nu is a source that if the functional derivative will give you the 1-point function, and CH is can be understood as like a heat capacity when you do thermodynamics. And the point of this is that you can take this action and compute the equation of motion for the diffeomorphism Fu, and you will find a third order ODE. And this is the famous result from Jensen and Juan and other people a lot of years ago. Okay, so the point that I mentioned before is that I want to compare with the UV theory. The UV theory is higher dimensional, and there is not such a thing as a representation mode. So I need to find a language that is more universal across dimensions. That's why I'm going to introduce the word identities. To introduce the word identities, I need to introduce an extra variable that I'm going to call O tau and do this de-identification with the Schwarzian and the source nu and define like O5. If you do that, you instead of getting one equation, you get two equations. And if equation, you will get back to that third order ODE. So in this case, one thing extra that I did in this step is that before I considered that the 1D matrix was just du. Now I consider like a curve 1D time, and I introduce this alpha over here.
Sorry, Robinson, when you talk about word entity, you usually talk about asymmetry. And here the symmetry is like it's not a gauge symmetry, it's an internal symmetry, like the SL2R that you have in the Schwarzian theory. You're talking about that symmetry when you do the word entity.
Like here I talk about gauge symmetry, you are right. So essentially this comes from diffeomorphism variance in the one-dimensional space-time. And this becomes because the Schwarzian theory is anomalous under Weyl transformations.
But the Schwarzian theory, the SL2R symmetry that you have in gravity, in the Schwarzian theory is in the target. It's not in the space-time.
What I mentioned is the gauge symmetry, is not the let me think. You are talking about the gauge symmetries that you have over here, right?
Yeah.
Yeah. I know that there is a LS2.
You mean the reparametrization symmetry?
Yeah.
Okay.
But those gauge symmetries are different from the gauge symmetry that I mentioned here.
Oh, okay. So this is not the same as the previous slide.
No.
It's another model. Okay.
No, it's the same model. It's just different gauge symmetries. This is the Schwarzian theory, but the point is like if you combine diffeomorphism and Weyl symmetries, and you require that they cancel out, you will find some kind of Virasoro, and the global power of Virasoro is LS2R.
Yeah.
I'm not focusing in that part because the point is that part will not something that I can compare with the UV. So instead, here is I emphasizing the diffeomorphism and the Weyl symmetry.
But in one dimension.
In one dimension.
Okay.
So then you can ask what is the generating function that is able to give me these word identities, which is the following expression. So here, if I implement a diffeomorphism or a Weyl transformation, I'm gonna recover the equation that are in these two equations over there. And this was done at the same time that Juan and Jensen, but by Ioannis and Miriam, 2016. Okay, so essentially it's kind of, you might think beyond of symmetries argument. I dislike this equation because it's a third order. If I want to transform that equation to become first order, I need to introduce an extra variable. That's what happened over here. And this matches better with the diffeomorphisms, Weyl symmetries that I understood better in higher dimension. For that reason, I prefer this language to compare in higher dimension. Okay. Now, this is the Schwarzian theory written in just a different way. Now, I started talking about gravity. This is the famous JT gravity. I want to translate those word identities to the bulk. In other words, I want to find what metric configuration is able to reproduce those word identities. So give me a moment. this is when you need to be very good with symmetries and asymptotic symmetries and those kind of things. So what I did over here to do that is like, okay, first of all, in holography, the radial direction is basically the energy scale. So I need to find a gauge where the energy scale becomes very simple. So in this case, means I want to impose that the dilaton is linear in R. Okay, and nu it will become some PVH transformation that will induce a Weyl transformation in the boundary. And the question is, what gauge is able to do this? Is essentially Bondi-like gauge. In this gauge, I can impose this form of the dilaton. So then this is my Bondi gauge, and now I need to find a way of finding the F nu, F1 and F naught, such that when I use the equation of motion of this theory, I'm gonna reproduce the Ward entities that I showed you before. So those functions are this one over here. So here I have the operator O5 and O tau that I showed you before, expressed in terms of F1 and F0. So if I introduce this to the equation of motion and work out everything, I'm gonna recover these Ward identities after the identification that the heat capacity is L2 over kappa 2. Newton constant in 2 dimensions and the ADS radius. Yeah, so maybe I didn't say something before, is that the reason that I introduced the sort alpha here, make this one line curve, is because alpha is the dual source of the operator O tau, and nu is the dual source of the operator O5. So that's the reason why I did that. So in this way, what I told you is like I re-express the Schwarzian derivative, the Schwarzian theory in a way that is more like a more universal language of the Ward entities. I then I build for you a line element that is able to reproduce this Ward entity through the equation of motion of the gravity theory. Okay.
Robinson, here F1 is the boundary term of SS of the JT action.
Just an arbitrary function. It's a bad notation. I should change that. It's not this F over there. This is F is just temporal diffeomorphism, and here F1 and F0 are just arbitrary functions that I need to use in the equation of motion to find the Ward entities. Okay.
So this is a convenient parameterization. You have to put this in the boundary term of the action or something.
No, actually, this is so beautiful that you don't have to evaluate the Mancilla action at all. What I'm doing here is say, this is again an intuition from holography, that basically when you have the Einstein equations and you push them to the boundary, they become the Ward identities. More precisely, when you have the canonical momentum associated to the Einstein equation, you push that to the boundary, it will become the Ward identities without relying on going to evaluate the Mancilla action and all of that.
Okay.
So that is very important for what I say later, because at the level of the action there is some problems. But here this is just a different way of doing the same thing that normally we do with the Schwarzian action.
Yeah, usually one evaluates the ansatz that you use for the metric on the boundary term of the metric of the action, and this gives you the Schwarzian.
Exactly. That is the way of doing that. But at the level of the action between the IR theory and the UV theory, there is some problems. So I want to shortcut those problems, and because of that, I have to do it in this way. So because here you have, so for doing this, you first of all you need to, every solution must be locally ADS2, right?
Yeah.
Essentially, this metric satisfies that.
Yeah.
But then the other equation is the equation about the dilaton. And when you work out that dilaton equation in this parameterization, what you obtain is these Ward identities.
The dilaton is that the leading term, right? You can have corrections to that, right?
Depends on yes, but that correction I can remove by gauge transformation.
Okay.
By gauge choice, I can make that dilaton is the radial variable.
Okay. Thank
So
you.
And the way that I'm doing this is to emphasize a lot of that the dilaton must be linear in the radial variable, because I want to think that the radial variable is the energy. So I want to do some kind of energy flow across dimensions, and I want to track the energies essentially. That's the reason that I do all of these choices. Okay, so now I have to do the same in higher dimension. Yeah. So in the article, we consider different CFT, but for today, I just gonna focus in the not the simple one, but in just one case that is CFT3 with a U1 current. So it's a holographic CFT. I don't know what is the matter content precisely. I don't care actually. The only thing that I care is just symmetries. The universal sector given by current loss. So in that sense, if I consider the stress tensor with a U1 current, this is the generating function because of just symmetry arguments. From that generating function, if you implement that is invariant under diffeomorphisms and U1 current, you will find this conservation, what is the name of this? I mean, the conservation of the stress tensor and the conservation of the U1 current. And because this is a CFT, you will find that the trace is 0 in 3 dimensions. Okay, so also means that I deal with the diffeomorphism, Weil symmetries, and U1 symmetry. Okay. Now I need to pick out a particular background for the metrics and for the vector potential, because they are background fields that I want to describe. So here's when you need to pick out whatever you want, depending on what you are doing. So here I consider a fixed background in 3 dimensions that have this piece that look like 1 dimension plus a transverse space. That is this one over here. Nu is a Weil factor of this transverse matrix over here. Okay, and then I just give it a very generic vector potential, where mu is essentially the chemical potential associated with the electric current. The next step is that, so essentially these background metrics, the gauge fields, are the sources for the stress tensor and the U1 current. So now I'm gonna decompose the stress tensor of the U1 current in terms of this choice that I did for the background metrics and gauge field. If you do that decomposition, this equation over here becomes the equation over here. Okay. And in that way, it starts to look like what I did in JT gravity. And to obtain that expression, I have to do a very precise decomposition of the stress tensor and U1 current. That is essentially this expression over here. So here I am just renaming things, like I haven't solved any equation. This is are the component of the stress tensor, and then I introduce notation such that I'm able to find the sources to these dual operators. Yeah, the geometrical sources, for instance, my nu that was kind of a bifactor is dual to the transverse operator. Alpha, that is the dual relative time, has this other operator, and so on and so forth. Okay. And also I have a electromagnetic field here, and I want to introduce a magnetic charge. So here, this is the U1 current. The first component is like it's kind of an electric operator, and here is like a magnetic operator. All of these functions depend on U, C, and C bar. Again, I haven't solved any equation, just using a smart notation. Then, if I express in that notation, in that parameterization, the word identities, I got this expression over here. So, for instance, you can see the trace condition. The traceless condition in CFT3 written in that way. This is the U1 current conservation, and then the other components of the conservation of the stress tensor. Okay. Here, I emphasize a lot of that I haven't solved any equation. Actually, no one knows a general solution for this equation over here, because essentially they are literally the full Ward identities of the CFT3. If you think this in terms of gravity, means that in 4 dimensions, no one knows how to solve the Einstein equation in general because it's a nonlinear theory, right? Just is a smart parameterization. Now the point is, the following step is to say, I need to find a gravity phase space such that I'm able to match these Ward identities. The problem is that in 4-dimension in gravity, there is no way that I'm able to deal with the Einstein equation because they are too hard. So I need to find a pseudo space that that is embedded in these Ward identities because that will be easier to deal with, not the full Einstein equation that is too hard to deal with. Okay. Is there any question up to this point? Okay. So let's move on to gravity. So now in gravity, I consider a 4-dimensional Einstein theory with a Maxwell field because I want to discuss near-extremality. And again, I'm gonna introduce what I call a UV dilaton without doing any dimensional reduction. So I want to say what gauge I can consider where the dilaton becomes proportional to the radial variable that in my holographic mindset, it means the energy scale. There is a source that is able to induce Weyl transformation in the boundary theory. And also there is a point that I consider like a energy scale of reference. So essentially this is a translation that I can do. This is a Weyl transformation that I can do in the radial variable. And again, in higher dimension, the gauge that allows me to do this is something like the bundle-like gauge. So now what I have to do is say, okay, this is a very generic gauge. I have to impose a certain asymptotic behavior for this function that must match such that I'm able to match the boundary metrics. It must be alpha, and this B must go to 0, otherwise I am not able to match the boundary metrics. So now I need to introduce this to the Einstein equation and solve the radial direction because that is the energy, and the transfer dynamics must become the Ward identities that I showed you previously, or a subset of those Ward identities. The parameterization is horrible. I think at this point you weren't able to follow the algebra because it's a lot of things that's going on in the middle. But it's something that I can do very explicitly, and I have control over that. Okay, and this is the Ward identities that you find through the Einstein equations. And these equations are not the full Ward identities in the CFT3 because the Einstein equation is too hard. But it's a subset that is still off-shell. I haven't solved any equation. Okay, and actually this space-time is called the shared ADS Robinson-Truman, but I generalize those space-time in several ways. So you can call it Robinson-Truman space-time if you want. Right? Here, essentially, the generalization means that I'm able to impose that. Normally, when you work out in ADS4, you assume the trellis condition of the boundary stress tensor in your solution. But here, for instance, I'm able to obtain the trellis condition through Einstein equation, not on shell. And also here, I modify the boundary in many different ways. So in that regards, it goes beyond of the usual Robinson-Truman space-time. And the Robinson-Truman space-time, to have some kind of physical intuition, is some kind of a space-time with radiation that in the future, a very long time, it will settle down to ADS Randi-Nordstrom black hole. Okay, that's kind of the physical intuition of this system. If I want to compare these Ward identities with the previous thing that I showed you in the CFT3, you need to work out certain identification. Essentially here, those operators OQ and OQ bar that appears over there are some kind of complex variable of the electric and magnetic operator. And in particular, OQ is holomorphic. OQ bar is anti-holomorphic. That is something about the building Robinson-Truman space-time. And then the stress tensor must take this particular form to match with the CFT Ward identities. That means that this is not a full expression, but it's still enough offshell for the purpose that I want to do with. And I have similar expression for the electromagnetic sector, but I think you want to see those expressions, right? So now I have word entities and light elements that is control everything. This is the UV theory. Yeah. Is there any question up to this point? So if you notice, I am building everything such that I am avoiding to use the action, the on-shell action. Later, you will see why that is very important. Okay. Okay, now I have my word entities. I have the geometry that is able to do all of this. I have to implement the decouple limit. So let's discuss what is the mindset behind of this decouple limit that I'm gonna call it offshell because it's a generalization. So this UV dilaton, as I'm telling you, is I haven't done any dimensional reduction. It's something just a radial variable from a higher dimensional point of view. But normally that's what we call dilaton. And it's built such that this is kind of a Weil factor, and this is a reference scale of energy. So if you think that this is, I am talking about energy, what I'm gonna do is to refine nu. It will become lambda nu tilde. And then I'm gonna take lambda to 0 with nu fixed, such that I am doing assuming in this arbitrary reference scale of energy. So that is the way that I'm gonna implement the RG flow in this context. Okay. And then if I do this, I'm gonna get a lot of divergences at the level of the geometries and the background and the metrics and the background vector fields. So I need to give a prescription to remove those divergences. And also, without any prescription, the word identities will become a towers of differential equation that are coupled. So I need to find a prescription that give me control of those in this procedure. So the prescription is essentially what we do in this context. Like we fix charges. Like when you do the couple limit is with the charge with fixed charges. That's what I meant in this context. And this content means to fix this operator OQ. By dimension analysis, I know that this operator OQ will go with 1 over lambda. Then I take lambda to 0. This choice is only possible if the function J's that I had before, that represents radiation in the bulk, becomes holomorphic function. Otherwise, it won't work. So that's in my prescription. And then the rest of operator that appears in the word identities and in the metrics, I'm going to expand it in a Lorentz series. I know that the Lorentz series is cut in the order 1 over lambda because of dimensional analysis. So this is essentially the way that I'm going to implement the decouple limit. It's fully offshell. I haven't solved the word. Yeah, I haven't solved the word entity, so it's completely offshell. Okay. So I'm going to do the geometric expansion, essentially expanding the metrics and the vector potential. If you do this, you will get some terms that will blow up, except that you are able to define these terms like this. Essentially, the operators that were offshell are picking at a particular values in terms of phi naught and L, the radius L4. And that means that if you are not familiar with doing this, you will see that these conditions essentially are the extremality conditions of ADS4, the ionic Riemann-Nostrum blatt, just written in a language that is unusual. So it means that the regularity conditions in this decouple limit is essentially that I had a fixed IR fixed point, that is extremal Riemann-Nostrum blatt. Okay, so other regularity condition is that this JC that was kind of the bulk radiation must go away, must be 0. So it must be just extremal black holes. And this transverse matrix, at the beginning, it could be a very complicated arbitrary transverse matrix, but now it becomes just the true sphere. Because this IR fixed point is essentially just a Riemann-Nostrum black hole at extremality. And then on top of this IR fixed point, I'm gonna have some like linear geometry that is essentially given by this affected matrix over here. This is the last function of the affected metric that I'm gonna get. So that I get through the decoupled limit. So if you see this expression, yeah, here you will have the typical leading order in the last function, and this term over here is essentially the ADS2 radius of ADS2 radius, essentially. So here I start to look like ADS2 cross S2. So yeah, this is the last function of ADS2 times this S2. And then, okay. So that means that I'm able to identify which is the ADS2 radius. And the other thing is that I'm also able to identify what is the the IR dilaton. So the idea is that this point over here is essentially the radius of the extremality of the usual black hole. And this small fluctuation on top of that radius is the IR dilaton. So this is the dilaton that we have in JT gravity, essentially that. Okay. So if you see through this decoupled limit that is off shell, I didn't assume a spherical symmetry. Regularity condition is telling me that I have to end up in a spherical symmetric configuration with this dilaton.
So, Robinson, sorry to ask at this point, but I don't understand in the end if we are in the field geometry or we are like expanding in the near extremal solution, because there you have like an expansion and also you impose or look for solution of that looks like the Schwarzian modes. So I thought you were going to have like to find that kind of solution when you take some limit, but I got a bit lost then if you are.
Yeah, maybe the notation is kind of complicated, but when the decoupled limits means that I'm gonna do a Bell transformation such that I'm gonna zoom in this arbitrary constant over here. And that way I have to span all of the operators at the level of the metrics and also at the level of the word identities.
Okay.
So when I do that, I found this regularity condition over here.
So, but you're expanding then near the phi 0, that is the extremal solution, you say, the fixed point.
You are starting from the UV theory, and you are giving this prescription, and this UV theory is landed in S2 cross S.
Okay.
So I didn't start from the extremality, I start from the UV.
Okay.
And then this decoupled limit is self-consistent such that you will land it in ADS2 cross S2.
Okay.
Yeah, if you see this, the transverse, as I told you, the transverse function will become S2, and this is the ADS2 matrix essentially.
Okay.
After the decoupled limit, so many things goes away. Or here there are other higher order correction in lambda that I am dropping away. Okay, and that's what happened.
Thank you. Okay, thank you.
So that way I can recognize what is L2 and also what is the IR dilaton. And essentially this constant that at the beginning was completely arbitrary, by consistency of the decoupled limits becomes the streamer radius, essentially, of the black hole. But then this is just the geometry, right? I also have to span the word identities. So if you span the word identities, you will find these two equations. So I have all of these like 4 line of equations in the CFT3 that will look very, very, very complicated. But then after doing this expansion in a small nu essentially, because that's what I'm really doing, many times goes away because at this order, and you get a very simple equation over here. So essentially, from the word identities from the CFT3 at a very low energy, those are what the equation that survives. And they are optional. I haven't solved anything. Okay. Yeah. So yeah, now is where the puzzle comes from, because it's like, okay, I did all of this. What is the next step? So here's the situation. So here you have the word identities in JT gravity that at the very beginning I show you what I claimed that were equivalent to the Schwarzian dynamics, or the expression over here. And over here, I have like what survived from the Ward entities in the CF3 after the decoupled limit, which is essentially this expression over here. Okay, and I know that I was able to obtain the right IR fixed point. That when I did the decoupled limit, I started from the UV, I flew, I landed in the extremal ABS Reynolds-Armstrong black hole. However, these Ward entities that are the fluctuations doesn't look like JT gravity. Like if I compare these two equations, the first one looks nice, but the second one doesn't look correct, right? Somehow the fact that the CFT₁ doesn't have anomaly is reflected in this side of the expression. There is zero. There is not anomaly in the CFT₁, even though now I am in the regime of low energy. And this becomes a little more confusing when you realize that even though I went through the Einstein equation and do some geometrical stuff, actually you can do this just starting from the CFT₁, making some few assumptions and expanding the Ward entities of the CFT₁ and getting these Ward entities without invoking gravity at all. So it starts to look like what's going on, what goes wrong. I am really getting JT gravity or not? Okay. Do you understand the puzzle, or do you want some clarifications? Okay, so now the idea is try to solve what happened, what we are doing wrong, or what's going on here. So here I just can compare the Ward entities that I got. So a part of those Ward entities, I also have the generating function. So I can see at the level of generating function what happened over here. So yeah, before jumping to the generating function, I just want to emphasize again that in higher dimensions, if you have anomaly or you don't have anomaly, it's a well-defined question that you have or you don't have. There is no middle situation. So in other words, if you have anomaly, there is no way that you can remove the anomaly. Okay. For instance, in the CFT₂, because of the Cardiff formula, the anomaly matched with entropy. So if you try to remove the anomaly, you will have trouble with the entropy that is observable and so on. So you cannot do that. Well defined. Nevertheless, the Schwarzian theory is not a CFT, but it's a conformal perturbation around a fixed point, a trivial fixed point. So maybe that's open the door to do something different, right? So maybe one of the main lessons that I will that you keep in mind is that Schwarzian theory is not a CFT. So here I have, instead of the Ward identities that I obtained through this procedure, I can compare the generating functions. So this is the generating function of JT gravity that will give me the correct anomaly. And here I have the low energy CFT₁ effective action that will give me the Ward entities, but without anomaly. So the question is, in other words, what I'm saying here is that this effective action, this generating function transform anomalous under Weyl transformation, while this other generating function is invariant under Weyl transformation. Essentially, that's the statement at the level of this point. So the question is, am I allowed to add a content term such that I can induce a field redefinition between operator and able to recover the anomalous behavior of JT gravity? If you add that question in higher dimension, the answer is no. You can never do weird stuff with anomaly. The anomaly are genuine, okay? But the Schwarzian theory is not a CFT, so I have more possibilities. And the answer is yes, you can do it. So essentially what's going on here is that you need to add a counter term at the level of the action that will induce a field redefinition between these operators, a mapping between these operators and this operator over here. Okay? And this is the content term that you have to introduce. Here in this talk, I just focus in the case of CFT₁ because I think it's easier to understand what's going on. But I also, in the paper with Alejandra and Ioannis, we work out other cases like the CFT2 with equal central charges and different central charges, where you have essentially in gravity higher derivatives. In that case, gamma will have a different value. But the point is like, yeah, this is the contenter that you can introduce here to deal with this. And the mechanism that I told you right now, this construction is very generic. So I'm telling you in the paper, you will see that other cases work out explicitly, but I can consider a phase space, a gravitation phase space where you have a rotation and the construction will go through and you will have, it will, for instance, CFT3 will be the same contenter. It's more something about the theories than the solutions. Okay, and this is very generic. You can do it in higher dimension rather easily, conceptually easily, because then you will have some technicality issues, but that's other story. Okay, yeah. So this is the contenter that you need to add. But now this contenter is kind of what's going on here, like I don't know, like our intuition for high dimension is wrong, essentially. Like, since the Schwarzian theory is not a CFT, we have more freedom to do things. Okay, and if you want to see this field definition that I talk about explicitly, is the following. It's over here. If I pick up this OU operator and OCC bar operator that I start in the CFT3, I do the decoupled limit, and then I introduce this field definition, I'm gonna able to reproduce the Ward identities of JT gravity. And this field definition, these extra terms come from this contenter over here. Okay, so there is a clear mapping between the CF3 variable at low energy with the JT variables in such a way that I'm able to go to the Schwarzian theory as I should be in lower dimension. Is there any question to this point?
Robinson, and when you add this control term, you're adding it in the CFT3. Since okay, you say that the Schwarzian theory was on CFT, so if you want to match things, you are like modifying CFT3 to match the Schwarzian theory. That's like the idea that you're trying to do, right?
But the point is like, here it looks like that I in this by hand, but the point is like remember that someone have to do this early flow in the fifth theory. That is really hard. Like normally you cannot do that, right? So and the CFT3, you will start without known anomaly. And when you do this early flow, because of quantum effects, somehow these contenters will appear naturally.
Okay.
That's what gravity is telling you that will happen. That's essentially what I'm saying.
Okay, because my question was going to be how to interpret this control term from the gravity point of view, but then it doesn't. I mean, because yes.
Actually, for instance, this mapping over here is also, you can see at the level of the last function that when you do the couple limit, since you will have the last function from the pattern theory, then you can compare with JT gravity, and it will tell you that you have to do this mapping. So essentially, gravity is telling you have to introduce this counter term because gravity geometrized the energy flow.
Okay.
Now the question is, from the field theory, what happens? That is the hard question. It's essentially kind of the discussion over here. If I am a field theorist, it's very unlikely that I'm gonna introduce this content term if I didn't know gravity. Like, it's just magical. So essentially, where this content term is coming from, I don't know. It's just gravity is acting like a black box. It's just too smart that I don't understand what gravity is doing. It's just giving me the right answer. And also, the assumption here is that I'm assuming that the Schwarzian theory is the right theory in the low energy. So because of that, I have to impose this content term. I have to introduce. But the idea I would like to go to some expert in field theory and energy flows, like for instance, Zohar Komarkovsky, one of the guys that proved the A theory in 4 dimension, and ask him, what's going on. Do you know an example in QFT or quantum matter physics on gauge theory where something similar happens that I can try to grab some intuition for field theory or not? Because it's too magical. And actually, this question over here is why my paper hasn't been published in the last, I don't know, more than 1 year. It's just trying to look for in the literature what could be some analogy that explain this. Like we didn't find nothing. Like we have this computation for a lot of time ago, months and months, but it's just this kind of question, this kind of weird stuff that we got the struggle by more than 1 year. The other thing that you can say, and that is too radical, but it's a logical possibility, in my view, the UV theory is casting doubts on whether the Schwarzian dynamics really capture the near horizon degrees of freedom. Like, I don't believe in that. It's too radical. I think I am a believer of holography, so that means that gravity is right. We should trust in that. So this constant term must be imposed by hand over there. It looks like that must be imposed by hand, but it's supposedly some quantum effect that happened in the energy flow that it would induce that constant term. But it seems to be like a logical possibility at this point. So that means that we need to understand this better from the point of view of field theory. And also, because of this logical possibility that I don't believe, we should also, that this kind of the conclusion is like most from the point of view of gravity, that the thing that I can really work out and understand better is we need to find more evidence that actually a very low temperature black hole scale like this by using the full geometry without relying on the near horizon approximation. And in particular, we have to do it for d bigger than 4, equal or bigger than 4. Because in the lower dimensional case, for instance, in ABS3, you have beta 0. So beta 0 is normally is very good, but also induces maybe some confusions, or maybe, I don't know. I believe in beta 0 and all of that. More evidence for higher dimensions. So something very pressing to really trust in all of this computation is to work out this logarithm correction in Reynolds-Nostrom using the full geometry and find the correct scaling. That's kind of the thing. I think, yeah, that's kind of the conclusion of the talk. If there are any questions?
So at the end of the story, you did a lot of redefinitions. So it's a little bit hard to follow what was what in the story. But what's the Schwarzian theory from the 53? How do you see the duplicity in this case? How do you know that you are doing expanding around this fixed point in the 53, or what are you doing? How do you see the Schwarzian theory coming up from the UV?
Yeah, for instance, this is the Ward entity that I got from the CFT3, right? This decoupling limit that I implemented, I can just do at the level of Ward entities by assuming certain regularity conditions that will appear at the level of the generating function. But I can just implement this, and you will get this without relying on gravity at all. The point is, like, from the field theory, there is no way that I'm gonna figure it out that I have to do this field definition. That's kind of the lesson, at least as far as I know. So that is when you need to go to gravity and ask what's going on, and gravity will tell you, you have to do it.
And what is the temperature in this equation?
This is in real time, in Lorentzian time. I haven't talked about temperature, but you have to do some Euclidean and with rotation, and you will able to see temperature.
But when you will rotate, you take the real line instead of the circle, the thermal circle. So how do you make it appear the beta?
No, just typical statistical physics. Like you just rotate, and the temperature will appear.
And here you seems like you will want to make OT equal to OU, OV equal to OZZ.
Yeah, that's naively what we will do, right? That identification.
But in the right hand side you have a 0, and up, you have a dependence of the temperature. So here's
Where is
how do we
team?
CH, yeah, over
Yes,
that.
heat capacity
doesn't
is a
appear.
parameter that when we are in thermodynamics, we consider that the heat capacity, but it's just, let's say, a coupling constant.
Yeah, but it doesn't appear in the
Exactly,
equation.
it doesn't appear, right? So someone from field theory will be very confused, will claim that there is not anomalous dynamic. That is the puzzle, like if you just do field theory, you will miss the anomalous behavior. And if you miss the anomalous behavior, you won't see the Schwarzian theory.
So yeah, so you added this counter term, and this counter term would make this 0 goes to
To become this essentially.
this. Yeah. Okay. So this
Without ruining the first equation, without destroying diffeomorphism.
no, but this counter term that you adding is breaking the safety symmetry.
Yes,
Okay. Explicitly.
yes.
Okay.
Yeah.
Okay.
So like the point is like, because I can do this just at the level of one entities, I'm gonna get very confused. No one will tell me that I have to do this, right? But since I was able to generalize the couple limit in a very explicit way, I can go to gravity and ask what's going on here. And gravity will tell me, no. You cannot say that, oh, tau is equal to OU. That's wrong. You need to do some field redefinition such that these two equations will preserve, but then here will appear some anomalous coefficient.
But isn't this the same that adding a defect to the theory?
No.
Intensive 3. No, it's not the same. Okay.
Now this is something that is normally when we do RG flows, new constant terms appears and new low energy variables also appears.
Yeah, but yeah, but this is what you are saying, that there is no motivation other than you want this to match to add something there, because you don't have a conformal anomaly, you don't have a I mean, if you want it to match, you can add it, but I don't follow the necessity to add it, but be in intensive trip without looking at gravity.
Yeah, that's the point. Like, it's very unlikely that someone from just doing field theory will rely on this. That is the point also why maybe people from the 1997 when Juan got holography and they say, oh, AD2 is too complicated, happens, I don't know, 20 years or more, and no one see this. Because it's not obvious at all, right? There's no way that you will have this insight from the point of view of safety.
Yeah, but I don't understand if you forget about gravity, you want to add it. But what's the meaning of this that you're adding, of this term?
The point is like just from safety, I wouldn't
Yeah.
do that.
No, add it. You yeah, do whatever you want. You add it. But
If I add
what's
it
the
will become
meaning
Schwarzian
of
theory.
adding this in the safety tree?
If I add it, it will become the Schwarzian theory.
Yeah, but why?
It will means that I explicitly break the conformal symmetry around the IR trivial fixed point.
But you don't have. I mean, it is a CFT. CFT doesn't have an IR or UV, right? It's,
In the UV, it's a CFT, but when I induce the RG flow, the theory will flow. So I don't know what will happen in the IR, right?
I mean, but it's a little bit confusing to me. Why it is a this is a CFT tree in a principle, right? If you don't
in the
yeah,
UV, right? In the way that we build QFT, we start from a fixed point in the UV. In the IR, there is another fixed point. When you are doing the flow, it's a QFT because you're breaking just in the fixed points. There is a scale is better, right?
but it's flowing because of this term that you added.
No, it flowed at the very beginning when I did the couple limit at the level of
Okay.
it started to flow, right? Since I am doing this couple limit, I am breaking certain symmetries.
Okay.
And that point is where you just lost the scale invariance, and then you don't know what is the end. So if I add these content terms, I gonna notice that actually is a explicit breaking of the CFT1 essentially.
Okay.
Now there is an intuition that it doesn't follow from IUV completion. It just follow for general consideration of condensed matter physics and effective field theories. Like when you are at a very low temperature, quantum fluctuations start to dominate, and sometimes happens that some symmetries becomes anomalous. But that intuition doesn't give me the right prescription to do this, right? From field theory.
Mhm.
So essentially, kind of the lesson is that gravity is too smart.
Okay.
Now we need to
Mhm.
find a smarter field theory guy that can tell us why this is obvious. And it's not something too mysterious, but I don't know what.
Robinson, can you repeat the conclusion? I mean, I forget why you say that we need more evidence that the Gaussian mode basically are in the near horizon limit of a black hole, but we need to do the full geometry computation to gather that information. Why you say that?
It's because if you don't believe in holography, there are people that do not believe at all in holography. Will tell me if UV theory is telling me that this is zero means that there is not anomalous dynamics. That is
Okay.
the end of it. So someone can very radical that hates holography will claim that. So there is no such as Schwarzian dynamics. But for sure I don't believe that because I'm a guy that works in holography, right? So in other words, to avoid that problem, it will be very nice if we are able to compute this famous behavior of the partition function of black holes using the full geometry without relying in the Schwarzian dynamics. So in that way, it will be clear that just true.
Okay. That time confused me a bit because at some point, wait, okay.
Maybe the point is that people, when compute this at very low temperature, this behavior of the partition function relies in the near horizon approximation,
Mhm.
not full geometry. Exactly because of that, it's like Chiara and Mashek and Joaquin started to try to do the same computation using the full geometry.
Yes, that's what I was thinking on that because I saw Joaquin did in
Yeah,
three
but they did it
dimensions, the analytical, yes, and in numerical in four.
yeah, that numerical computation is evidence, but I wouldn't say that it's a real computation in deep form.
No, of course. Okay, I thought it was something more like, I mean, like the thing that the zero modes are concentrate from the four-dimensional or higher dimensional point of view, like in the near horizon limit. I mean, it's not that you have to take the. I mean, it's a different, right? I mean, if you consider the theory, the gravity theory, like in the field geometry, I mean, you have to search these zero modes that they are a common diffuse. And you will always you can always take this the Near horizon limit and see that this is like a large difference from the ADS2 point of view and start with the Schwarzian story and all that stuff. That's why for me it was like, okay, you can always take that limit. That's why I thought it was a more close story.
I mean, that is what we do always in ADS-CFT because ADS-CFT is essentially the throat from deep brains. So we believe in that, right? So the point is like, in this case, because ADS2 is more subtle, like the Schwarzian theory is complicated, right? It's not a CFT, but at the same time have a bit of sort of algebra, so it's kind of strange. So because of that, it's better to have different ways of getting the same result. Just make sure that there's nothing happen over there. I mean, I fully believe that this is true, like, but the point is like we have more computations essentially.
Okay.
So this line over here is just saying maybe it's a logical possibility that someone doesn't holography will claim. It's not me.
But re- ¿realmente existe alguien que dude de la grafía?
People that really hate string theory for sure.
But this is not true. Okay. It's come from, it's like, it's too in the past now.
Yeah, yeah. Essentially, it's
So,
that give me more funding to keep doing computations.
yeah,
This is very important. We need to check this.
okay. Anybody has any questions? More questions?
Can I do a very basic question?
Oh, wait, I didn't stop the recording. So let me
Okay.
finish the recording and we can start with more stupid questions.